All right. So different than absorption is photoluminescent spectroscopy or fluorescence. All right, fluorescence spectroscopy or phosphorescence, and this differs in a couple of ways. But the initial way, or the most pronounced way, is that if I have my sample, let's use a cuvette as a place where I'm going to contain my sample. All right, I have my light source here, and the light source is going to shine electromagnetic energy, and some of it would be absorbed, right? And so then your detector here would tell you how much light is being absorbed compared to a blank, and so forth. Well, if this chemical, or the chemical in here, the analyte in here, fluoresces or phosphoresces, then it will release those photons of energy in many different directions. All right. Now, do you remember why chemicals might release electromagnetic energy as opposed to just absorb that energy?
Well, you said that it could release energy by moving or by releasing what do you call a photon?
That's right, releasing a photon of energy. And so it is releasing that photon of energy because it has the energy and needs to get rid of it. Now, what did we say the relationship between the wavelength of the emission? All right, so this is our emission. And the wavelength here of the light that is absorbed.
You said that the emission had to be lower in energy.
That's right, because if it's absorbing at X, it's not going to be able to emit at a higher wavelength, right?
Yeah.
Okay, so absorption energy, the energy of the wavelength that is absorbed, will always be higher than the, sorry, we shouldn't say that. We should say the frequency, which is related to energy, for absorbed will be higher than the frequency for the emission, whereas the wavelength, because energy and wavelength are inversely proportional, right? The wavelength that's absorbed will be shorter than the wavelength that's emitted, okay? And oftentimes, the wavelength that's absorbed is very close to the wavelength that's emitted. And if that's the case, then fluorescent spectroscopy is not very helpful, because when your detector is here and it's trying to detect a certain wavelength, it's trying to detect a specific wavelength, the wavelength that's being fluoresced. If it can detect the light as it passes through there, I mean, if any incident light from the absorption it gets to the detector, then that can cause a problem. So fluorescence is only generally helpful, or is more helpful, when there's a larger separation between the wavelength of the light absorbed and the wavelength of the light emitted. Okay? So the primary difference between fluorescence and phosphorescence is the length of the emission. So fluorescence will stop immediately after the molecule is no longer being exposed to electromagnetic energy that it absorbs. Whereas phosphorescence, it will decay. We call the amount of energy that it loses. It'll decay very slowly, relatively slowly, and will continue to fluoresce, or phosphoresce now, right, for a significant amount of time. Okay, so here's what we were talking about, the relationship between the absorbance, the light that's being absorbed, and the light that's being emitted, right? And we need to make sure that there's this separation. If you're looking for the light that's being emitted at anywhere where this light is being absorbed, then you won't be able to get a good relationship between your analyte concentration and your signal. Okay, so absorption is along the x, the same axis as the source of the light, but Fluorescence or phosphorescence is off at a 90 degree or a different angle. It doesn't need to be exactly 90 degrees, but a different angle. Okay, so here's a good instrument model for a fluorimeter. And it's not terribly great, but same idea. Okay, for fluorescence, because of the extra movement of light, so here on absorbance, the light travels from here and goes out there. But for fluorescence, the light will travel here and come out here, and the fluorescence of samples will differ significantly from one to another. So you can have some fluorescence, some molecules which are thousands of, or hundreds of thousands of times more fluorescent than other molecules, whereas usually that absorption range is not so vast. Because of that, you have varying slit widths, the slit that allows the light to come into your sample, and the slit that is collimating the light coming out of your sample. And controlling those slit widths is usually what you spend a lot of time doing in preparing a method to make sure that your absorbance or your intensity, your signal, is consistent with your analyte. And the instrument that does this sort of thing is called a fluorimeter or a fluorimeter. All right. And that's as opposed to a spectrophotometer, which is looking at absorption from UV or visible or UV rays. Okay, let's see here. Now, fluorescence is extremely sensitive, and the sensitivity of fluorescence is such that they have what's called single molecule fluorescence. So if you have a single molecule in your cuvette or in your solution or your sample size, you can see fluorescence. And now, you can't get any more sensitive than that. I mean, you could get more sensitive if you could get more signal than the fluorescence could, and that's true. That's something that you need to look at. But fluorescence also suffers from what we call quenching, and there are other parameters involved as well. But a molecule can get overexposed, if you will, and then the fluorescence itself will kind of stop occurring, or fluorescence will change over time. And if you have an analyte in there and you're expecting the fluorescence signal to be kind of constant, it's not going to be the case. The fluorescence signal will decay over time, even as long as it's still absorbing light, due to what we call quenching. But there are so many different methods of utilizing fluorescence to identify the concentration of a compound. And you can learn so much, not just about the concentration of a compound, but its proximity to its neighbors, its orientation. There are shifts in fluorescence simply due to the rotational momentum or movement of a molecule. So there's so many different things you can do with fluorescence. It's a very kind of a very picky, or you got to be really careful about how you use it, but it can be very valuable if you know how to use it really well. You can make a career out of being able to understand how to use your fluorimeter well. Okay. So our inductively coupled plasma instrument is a type of atomic emission spectrometer. All right. So essentially, like we mentioned, you can flame, right, in atomic absorption spectroscopy. You can flame your sample and then shine wavelengths of electromagnetic energy that are produced by the element of interest, and the interaction between the elements that are created and the wavelength of interest related to the element interact, and you get an absorption property. But instead of just flaming it and letting it release like that into the air, you can cause create a plasma of your material, which is again very high voltage, very relatively high temperature, and low pressures, right? And from this plasma, you're going to get an emission released by the elements, just like we saw in the flame test video here, right? And that particular emission of those elements, the spectra that you see, will be related to those elements, and it'll be very, very fine spectra, not a very broad signal. And so it becomes probably the instrument and method of technique, or sorry, method of the preferable instrument and preferable method of use for industrial labs around the world, right? So to determine the concentration of metals and many other nonmetals, you'll see ICP, atomic emission spectroscopy used, inductively coupled plasma atomic emission spectroscopy. All right, and essentially it was working the same way as atomic absorption spectroscopy in terms of creating the light, but instead of creating the flame, but instead of shining a light through the flame, we're just looking at the color of the flame. So it's hitting our detector. And we have some pretty good detection limits for atomic emission spectroscopy. So for example, this is in micrograms per milliliters, or parts per million, right? And we can get down to 0.1 or 100 parts per billion here, right? 0.01, 10 parts per billion, very small amounts. Look at this for calcium, 0.1 parts per million or billion, or 100 parts per trillion, very small amount. All right, the instrument generally will do all the selecting of wavelengths, preparing the samples. You need to prepare the sample in an appropriate way, and this means usually in a slightly acidic solution, like a 2% nitric acid solution. And what this does is keeps your solution in, keeps your metals in solution, as opposed to precipitating out in the form of hydroxides. There's not a lot of, well, there is a possibility for spectral interference. You know, a lot of our discussion about interference before is very important to recognize when you're talking about atomic emission spectroscopy. However, software nowadays can look out for that interference and warn you of when two elements might interfere with each other. And there's lots of wavelengths that are emitted when a certain element is put into the plasma. So if you don't like the wavelength that is emitted because it interacts with a different element's wavelength that you're trying to measure, you can shift it and go to a different element and find out, or you shift it and go to a different wavelength that that element emits. So it's, again, something that's pretty straightforward and taken care of in your method development in the software. And hopefully we might have an opportunity to develop a method and run some samples on the ICP. Maybe not, but we'll see.